meeting window, then we'll see that you have come back to the meeting window. Your slideshow will become not visible.
I see.
Yes, sir.
Okay. I see.
Yes.
Okay, fine. Yeah. It's extremely impersonal. I think Zoom is much better than this. What do you think?
So we haven't actually used Zoom. We've been doing online classes on this for 2 years.
Okay.
So we haven't actually used Zoom.
All right.
Yes,
We'll see what happens.
yes, I think we can manage. Otherwise, for the second day, we can do a Zoom link for tomorrow, because today already the links were sent. But for tomorrow, we can set up a Zoom link.
Okay. Thank you.
Okay.
Thanks a lot. Yeah.
Yes. So, sir, I think for now you can stop presenting. We'll start when the talks happen. We'll do the introductions and all the formalities first.
Okay. All right.
Yes, sir.
Okay. Thank you.
Yes, sir. So I think we can just give a few minutes for everyone to start joining.
Okay.
Thank you, sir.
It will work now.
Okay, so I think can someone just confirm if I'm clearly audible on the meeting?
Yes.
Okay, thank you, sir. Then, good afternoon, everyone, and welcome to the 26th Annual Popli Memorial Lecture Series. Me and Sandra will be your MCs today. I'd like to welcome our honorary guest speaker, Professor Spenta Wadia, Mrs. Popli, and her daughter, Ms. Divya Popli, Professor Sanjay Jain, friends and acquaintances of Dr. Popli, our respected faculty, and of course, the students of the college. Dr. R.K. Popli was not only an esteemed lecturer of our college, but rather a mentor and far more to all of his students who are today themselves leading scientists. This annual lecture series, held in his memory, is the biggest event of the Physics Society and Department since Stephens College, Delhi. It aims to encourage curiosity as well as encourage discussion in physics, as was always Dr. Popli's endeavor. For the first time this year, the lecture series is happening in a hybrid online/offline mode. Professor Wadia will be speaking from TIFR in Mumbai, and the event is being live streamed here to an in-house audience in the new and old physics lecture theatres in college. This lecture series will consist of 3 talks given over the course of today and the following 2 days for approximately an hour each day. Professor Wadia will be taking us on a tour of space-time physics, Newton, Einstein, Hawking, and beyond. Dr. Popli left a mark on all of his students. And to speak a little bit more about him today, we have Professor Sanjay Jain of the Department of Physics and Astrophysics, University of Delhi. Professor Jain was a student of Dr. Popli all the way back in 1979 and was also a student of Professor Wadia, who was his PhD advisor. I'd first like to invite Professor Jain to speak a few words about Dr. Popli. Professor Jain?
Yes.
Yes.
Can you hear me?
Yes, sir. You're clearly audible.
Okay. Thank you very much. It's a great honor for me to be associated with this event, which involves 2 of those teachers in my life who made the greatest contribution, to my life and career in physics. I've been asked to speak about Dr. Popli, whom I first encountered in 1976 when I joined St. Stephen's College as an undergraduate student, a first-year undergraduate student of physics honors. And Dr. Popli taught me mechanics in the first year of BSc Physics Honors. And that is the only course that he actually taught me in the class or in the laboratory. But that course was truly transformative for me. I was interested in physics, but I wasn't quite sure whether physics would be my career. But after attending Dr. Popli's course, mechanics, it became clear that physics would be my calling. And Dr. Popli, he, I think, has transformed the lives of many people, through his teaching at St. Stephen's College. And the reason I think is the fact that he was, of course, a very gentle, kind, and considerate person, but also he was completely uncompromising when it came to the subject of physics and the understanding of physics as he expected his students to have. I remember him clearly, as he stood on the board with a chalk between 2 fingers and his thumb, and he's writing on the board, and he suddenly stops writing and turns around and asks a question. Okay. And this was a moment which was a very scary moment for everyone in the class, because you didn't know upon whom his gaze would come and stop, and who would be expected to answer the question that he has asked. Okay, so it was scary, but then he would help you to answer the question. He would help you to think clearly, and eventually, through that interaction, show you how simple it was to answer the question if you thought clearly and if you thought from the basics. And so, on the one hand, one felt very sheepish that, it's a simple question and one couldn't answer it, but or only partially answer it. But at the same time, it was very greatly empowering. The clarity with which he explained the point, the bringing together of diverse ways of thinking around the same point in physics, the bringing together of physical intuition with mathematics, the great beauty of physics, and the power of thinking with both physical insight and mathematical clarity. So this is what he was able to communicate, and through this, it became clear that here was an intellectual world that sort of opened up for me, and I could see the beauty and the depth of this world. And so was decided then to continue in physics, which I did later on. Apart from the fact that he was a brilliant teacher of physics, Dr. Popli was a man of great integrity and unflinching dedication to what he thought was right. And he was a very humble person. He was also deeply concerned about the students. He would want to know what is happening, what are you doing, and so on. And that abiding concern, together with his other qualities, was really something which affected you at a deep level. And so that was one, that is something that I would like to say about Dr. Popli. And I'm very fortunate to have been among the people that sat in his class and was taught by him. I should also mention that eventually that encouraged me to do masters in physics and then PhD in physics. And I went to TIFR Bombay to do my PhD in physics, where I came in touch with Professor Spenta Wadia. And Professor Wadia, who is one of the leaders in spacetime physics, and from whom we will hear today about the historical development right up to the present time of spacetime physics. There, very concretely, very slowly, introduced me to how to deal with the unknown. This is what the fact that the creative process, this is what Professor Spenta Wadia contributed to my way of my inner world, as to what does it depend upon, how simple examples on the basis of which you gather your intuition are extremely valuable in physics, and which allow you to then, how you pursue those doggedly, how you pursue your physical intuition doggedly, is the important thing. And how what matters ultimately so much is not how quick and smart you are, but how persistent you are. It matters upon, it depends upon deeper layers of your personality. It depends upon courage. It depends upon honesty. And it depends upon hard work. So, these are things that I learned from him, and participated a bit in thinking about gravity and string theory with him. With this, I would like to say again that I'm very happy that Spenta is giving these lectures, these Popli Memorial lectures, and how in my mind really this is a coming together of two different worlds of mine, and I'm very happy to be associated with this lecture. Thanks very much for inviting me to say some things about Dr. Popli and Professor Wadia, and that's all that I have to say for now, and please carry on. I look forward to the rest of the proceedings.
Hello, I'm Sandra. I will be your second MC. Thank you, sir, for your valuable words. Dr. Popli was truly an inspiration to many students. So today, we also have Dr. Popli's daughter, Ms. Divya Popli, who I would like to invite to say a few words about her father.
Thank you. Good afternoon, everyone. Professor Wadia, distinguished guests, and respected faculty members, everyone. It's an honor and a privilege for me to be able to join today this 26th lecture of Dr. Popli Memorial Annual Lecture Series. And it's an even greater privilege, and it was a real blessing to have Dr. Popli as my father and my foremost mentor. So I'm Divya Vanshika. I'm a proud alumna of St. Stephen's College, albeit from economics honors, and I'm currently the Director of Integrated Supply Chain Operations at Unilever. But I can tell you that my father would not have, really appreciated that job description at all. He never appreciated really, the molding of soaps or marketing. He was all about molding minds and, more importantly, mindsets. So he was an academic at heart and a scholar all his life. And St. Stephen's College gave him a perfect setting to pursue what was his calling, which was teaching and transforming lives through physics. If I start speaking about him, I could be talking for hours, but I think Dr. Jain has already talked about him so eloquently. So what I wanted to highlight here is that, not only did the college, with its very high standards of excellence, its brilliant students, and its absolutely awesome faculty members inspire my father in his lifetime, those deep connections have extended much beyond the classroom. And they enveloped us, his family, with a lot of warmth, even after his demise. He had a great personal connect with students, as Dr. Jain mentioned, and some of them, such as Dr. Sanjay Kumar, Dr. Vikram Phukan, were instrumental in organizing the Popli Memorial Lecture Series continuously. They made this event bigger and better with their immense and untiring efforts year after year. And I'm deeply indebted to them for making this a flagship event of the Physics Society. It's not just a signature event on the college calendar. It's a milestone event for all of us to really, remember his rich legacy and his values. So his close friends and colleagues of my father, Dr. S.C. Bhargav, Dr. R.K. Garg, Dr. Maini, Dr. G.S. Bhatia, Dr. Katyal, just to name a few, they took so much care of the entire family, and they assisted in every possible way when my father was unwell and suffering from cancer. And then even post his demise, they were the source of inspiration to really start the series. And among the attendees, who were always there to encourage the family and the students, there were his friends from the other departments as well. So Dr. Ishwaran, Dr. And N. Raghunathan, and many others. And the visionary principals of this college, Dr. Anil Wilson and Reverend Thampu, were not just gracious hosts for the speakers of the event. They were the bedrock of support for the event and always a source of strength. Now, keeping the legacy and the memory alive of someone who's passed away 25 years ago isn't really a simple task. But I think it is the St. Stephen's culture and DNA that has enabled that. And a number of his students, they still remember him very fondly, decades after passing out, and they connected with this series and with the family, and few have been a part of the series as well. So today, with this particular lecture series, we've got the opportunity once again to remember his vision of having a deeper understanding of the cosmos through physics. And while the principles and the understanding of the physics has evolved, as Professor Wadia, I'm sure, would cover in his lectures, from Newton to Einstein to Hawkins and others, what has been an unchanging hallmark of this event and St. Stephen's College overall is a culture of excellence, innovation, and research. And the spirit of curiosity and learning that this lecture series has always fostered. And I would sincerely like to thank the principal, the Physics Society, Dr. Sanjay Kumar, and the organizing committee for their immense efforts. It's a privilege to be here, and I'd like to thank you all.
Thank you, ma'am. I would like to take this opportunity to thank Dr. Popli's friends and family, whose continued support was also the reason that this lecture series was possible for the last 26 years. Your association with the college has been invaluable to the physics department and the college community as a whole, and kept the memory of Dr. Popli alive in all our hearts. Our principal, Professor John Verghese, sends his regards, but he's unable to join us today owing to a prior commitment. Sir sends his best wishes for the events and his thanks to our honored guest speaker, Professor Wadia. Now, before I start, I would like to go over the rules of the event. Those who are joined through Google Meet, I kindly request you stay muted throughout the duration of the talk. Any questions can be asked during the Q&A session or can be put in the chat box and it will be addressed later. For those sitting in the lecture theatre, you're requested to maintain silence throughout the duration of the talk. You can write any questions or doubts in the sheets of paper given to you, and the student volunteers will collect it from you so that your questions can later be asked during the Q&A session by the MCs. For those watching on YouTube live stream, you can put your questions in the chat box, and our moderators will ask them for you in the Q&A session. I'd additionally like to request the in-house audience to keep their face mask on at all times during the event.
Thank you, Sandra. I would now like to introduce Professor Wadia, our honored guest speaker. He's a celebrated Indian theoretical physicist specializing in string theory and quantum field theory. He's the Infosys Homi Bhabha Chair Professor at the International Center for Theoretical Sciences, ICTS TIFR, in Bangalore, and Emeritus Professor of the Tata Institute of Fundamental Research. He graduated with a BSc in Physics from St. Xavier's College in 1971 and a subsequent MSc in Physics from IIT Kanpur in 1973. He went on to the City University of New York, where he received a PhD in Physics in 1978. He's had an illustrious career in academia and research, primarily at the TIFR and ICTS, and has received numerous awards and honors, including the prestigious the World Academy of Sciences Physics Prize in 2004. He is the founding director of ICTS TIFR, a unique institution involved in furthering the boundaries of fundamental research and science education, emphasizing that science is one story. His areas of research include quantum field theory, statistical mechanics, string theory, and black hole physics. We're greatly honored to have you here today, sir. Before we start, I'd once more like to request everyone to keep their mics muted and the in-house audience to maintain silence during the duration of the talk. With that, over to you, sir.
Okay, I should share the screen.
Yes, sir, your screen is visible.
Yeah, just 1 minute. Is it visible now?
Yes, sir.
Okay. All right. So, should I begin?
Yes, sir. Thank you.
All right. So, thank you very much for this very kind invitation to give these Popli Memorial Lectures. Came as a sort of a surprise to me, and I agreed to talk to undergraduate students. Only when I started preparing these lectures, I realized what I had done, and it is very difficult actually for me to know whether I'll be getting across, but I am trying, and I'll try. Okay, so firstly, I am presently at the center of the Tata Institute of Fundamental Research in Bangalore. And you can see the institute actually in this picture. So we are very proud of it actually. Anyway, let me begin the talk. Okay, so the first part of the talk, there are 3 lectures, and the first part of the talk will be on Newtonian framework of physics and the law of universal gravitation. So I have prepared these lectures to give you both an overview, a perspective, and also some details, some small calculations, which I think are important. So here we have Galileo, a pioneer of the modern scientific method. And he discovered a new law of gravity. And that new law of gravity basically says that gravity acts in the same way on all bodies. They all fall in the same way, independent of their mass. And this actually, in some sense, as we'll see, implies that what you call the inertial mass of an object, that is its resistance to motion, inertia, is identically equal to what we call the gravitational mass, that mass attribute to which gravity responds. And these are identical. And this is a law of nature. It's experimentally verified, highly precise law of nature, which forms a very important ingredient in the general theory of relativity, as I will explain later. Okay. So now let's begin. So this is Isaac Newton, and he establishes a framework of mechanics. In this talk, I will be emphasizing frameworks, actually. Newtonian framework of Einstein, special and general relativity, the framework of quantum mechanics, and things that follow after that. So here, Newton formulated the laws of motion in terms of the flow in time of the position of a point particle in 3 dimensions. In 2022, this may look like a very simple fact, but I checked that it is only a little while before Newton wrote his Principia that the pendulum clock in Europe actually was sort of perfected. So this notion of timing the motion of objects and parametrizing it in terms of this parameter time is quite a revolutionary idea. And it, of course, borrows from the geometrical ideas of René Descartes, that you can associate 3 numbers which change along a parameter called time to, this is your framework. This is the stage on which the classical dynamics is sort of based. And so you have a curve, x of t, y of t, z of t. Can you see my cursor? Can you see the cursor?
Yes.
Okay, thank you.
Yes, sir. Visible.
Thank you. Thank you. So x of t, y of t, z of t is a curve, and the velocities and accelerations are given by time derivatives of the curve. You know all this, but there's no problem repeating the truth many times over. And so what Newton did was he unified geometry, calculus, and mechanics to provide a description of motion. One of the important things about Newton's framework is that time is absolute. And it's the same for all observers. You may be traveling in a train or an airplane or, in some other vehicle. We all measure the same time. We set our clocks identically. There is no difference. And this is a fundamental point of sorry, I think I lost something. Yes,
sir.
Yeah.
Yes, that's fine.
This is a fundamental point, actually, of Newtonian framework, that time is absolute. It's the same for all observers, whatever their state of motion is. And the last point is, on this slide, is Newton's laws of motion, that he invented a notion of a quantity called force, which has different origins, force of friction, force of gravity, force of electricity, whatever. And this is always equal to the inertial mass times the acceleration. And this is the foundation of all of classical physics. I mean, all of it. All of it means if you, for example, want to describe the flow of water, which today we describe in terms of the Navier-Stokes equation of fluid mechanics, they are all derivable and consistent with Newtonian mechanics. And this is also true of the kinetic theory of gases. It's also true of classical statistical mechanics, that the laws of Newton form a foundation for all of them. Okay, so that's the first thing I wanted to say. So Newton proposed the universal law of gravitation, and that law we all know, that if you have two bodies of mass m1 and m2, here m1 and m2 are gravitational mass, then the force between them is inversely proportional, always attractive, and along the direction that joins these two particles. Now, what is important about this law is the following bullet points which I've made. A gravitational force acts instantaneously at a distance. So you have two objects far away, one of them moves, the other one responds instantaneously. That's inbuilt into this law. It's always attractive. This is the only law of nature we know, the only one, which is always attractive. There is no repulsion anywhere, there is no charge screening, nothing. And the force, as I said, that's the Newton's law, is equal to the inertial mass times the acceleration. And then we have to put in what Galileo said. If we assume that inertial mass is equal to the gravitational mass, then the gravitational acceleration does not depend upon it. So there is a very simple way in which you can arrive at an understanding of what Galileo discovered in terms of Newton's law. And in the case of two bodies, this leads to the famous elliptical orbits of planets described by Kepler. I just wanted to say that what Kepler really discovered is he found a symmetry in big data. These days, it's very popular to talk about big data, but what did Kepler do? He looked at observations of planets by Tycho Brahe and other astronomers, a huge amount of data collected over years, and he was able to fit it into elliptical motion once he changed the coordinate system from the Earth to the Sun. So a modern way of putting the great discovery of Kepler, it took him 22 years to do this, is that he found this great symmetry in big data. Okay. Now, I want to give you two quotes from Newton, which are quite amazing, actually. So let me read them out. That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking would ever fall into it. Quite amazing, 1692. But in 1713, he says the following: I have not yet been able to discover the cause of these properties of gravity from phenomena, and I feign no hypothesis. It is enough that gravity does really exist, and acts according to the laws I have explained, and that in abundantly serves to account for all the motions of celestial bodies. You see, Newton was a very, very important person in the history of science, that he took experiment extremely seriously. So this, he says, basically, this is the law, this is the hypothesis. And what's good is that it explains the phenomena, experimental phenomena, and it explains them so well for the next several centuries. Within this domain of validity, it is even valid today. So these two comments of Newton are very important because, as we'll see, that the general theory of relativity basically addresses precisely these questions and explains many of these issues Newton had raised, actually, much before any of his contemporaries had really absorbed the importance of his laws. All right, now we jump a few centuries. So what was important in Newton's law was the action at a distance business, right? I mentioned that. That's very important. Instantaneous. That is, interactions are instantaneous. That's, of course, as we will see, is not right. It's a fallacy. And how to sort of cure that fallacy is precisely what I'm going to talk about now in the next several slides. So now I want to talk a little bit about electromagnetic theory, and you'll really realize why I'm saying this, because it is electromagnetic theory that provided basically the foundation of the special theory of relativity. So Michael Faraday had demonstrated that light is polarized by a magnetic field. If you pass light to a very strong magnetic field, it gets polarized. So there is a evident connect between optics and magnetism there. That is it's a very deep point, actually. Then, of course, James Clerk Maxwell unified electricity and magnetism, predicted the existence of electromagnetic waves, and identified light as an electromagnetic wave of oscillating electric and magnetic fields moving with a certain speed, which is 3.1 times 10 to the 5 kilometers per second. And he unifies electricity, magnetism, and optics. What is important for us, at least for this discussion, is that the force between charged particles is not instantaneous. It is transmitted by the electromagnetic field at the speed of light, which is finite. So it's like you have some very serene, silent pond, and you basically have two pieces of wood which are floating. Nothing is happening, and then you suddenly shake one of them, and the water waves transmit this shaking, and the other guy starts shaking. So this is the picture over here, which was not there in Newton's law of gravity. That forces are transmitted at finite speed and by means of some objects. And here it is the electric and magnetic fields. Okay. So the next slide is experimental tests of Maxwell's theory. It's always very important, actually, that there's good theory. And then I can't explain to you the grand beauty of Maxwell's theory, but I'm sorry about that. It's not much time. So in 1887, Hertz demonstrated the existence of radio waves. And in 1895, Röntgen made this famous serendipitous discovery of X-rays. So Hertz discovered waves which are much have much longer wavelengths than light, visible light, and Röntgen discovered those waves which have much smaller wavelength. And this idea of the electromagnetic spectrum now comes about by the end of the 19th century. Okay, so there is experimental verification of Maxwell's theory, and this is very important actually because I have here prepared a little tutorial slide because I was told that there are undergraduate students. I'm sure you have seen all this, but I cannot but tell you what these great equations of Maxwell are. And many of them were actually known from before. This is Faraday's law, the second equation, curly equal to time rate of change of the magnetic field. But it is this law of Ampere that moving charge particles produce magnetic field was modified by Maxwell in a profound way, and which is then consistent with the conservation of charge. And what I have done here in this slide is that I put these sources to 0, and I have solved these equations for you in a very simple way. So you have the electric field and magnetic field, they permeate all of space-time, and there are no walls, no conductors, nothing reflecting, nothing, no boundary conditions. And then the solutions are very simple, and what you have essentially is a wave. This is the wave equation over here in the last box, which is propagating in such a way that the electric and magnetic fields are perpendicular to the direction of propagation, and it propagates at the speed of light because k square is omega square upon c square. And this tells you that if you take the variation of the frequency with respect to the wave vector, you get a velocity, and that velocity is c. And it is the same in all reference frames. So I just thought, just give you this small little tutorial. I hope you don't mind me doing such things here. All right. Now, there is a very beautiful consequence of the fact that the speed of light is the same for all observers. It means the following, that if you run towards a source of light, and if you run away from it, the speed of light is the same. This is an astounding fact. And this is a consequence of Maxwell's equations. And this is why it is so important that Maxwell's equations have very, very solid experimental verification, actually. So therefore, this forms the cornerstone of the special theory of relativity. I'll tell you why. So it's a very simple thing that you find. I mean, I took this picture from the internet. I like it. So what you have is essentially some observer, maybe some space station or some place on Earth, and there is some rocket, and there is a person in the rocket, and this rocket is moving to the right of her at a speed v. Right now, there are two mirrors actually, and there are these laser beams, which keep on. The light keeps on oscillating between these two mirrors in the rocket. Okay. Now the question is, because the speed of light is finite, what does she observe? And it's so beautiful actually that what you have essentially is the fact that this rocket spaceship is moving at a speed v. So from here to here and here, we just go past this observer. But because the speed of light is finite, light will take a longer time to travel. And so you can just very simply apply this triangle theorem with this as the hypotenuse, c times delta t prime, where delta t is the time measured by the observer on the ground, and just write down this simple relationship and solve for delta t prime. So you get this very famous relationship between delta t prime and delta t, which says that the notion of time difference is not universal. It depends upon the speed at which you move. So in some very deep sense, because of the constancy of the speed of light with respect to inertial observers, space and time in some sense adjust themselves to bring this about. And it's an amazing idea actually. It's quite and this is the point which Einstein abstracted from Maxwell's theory, that it's a statement about the structure of space-time. This very simple things. Okay, so here is another simple tutorial. So there are these two reference frames, and they are related by they're moving with respect to each other at a certain speed. They're moving in the x direction for simplicity, and these coordinates and time observed by one person in one frame is related to what is observed by the person in the other frame. So I just put primes and unprimed t and x, and this is the famous transformation law, which was discovered by Lorentz, Poincaré, many people actually, in the context of Maxwell's theory. But it's Einstein actually who really appreciated that this is saying something about the structure of space-time. And here I have done something very well known, what everybody does, is defined as something called an angle phi. It's not an angle really, it's a number phi. And this is the hyperbolic tangent. It would be an angle if this is just the ordinary trigonometric tangent. And define V upon C by this, then this equations that relate xt to x prime t prime essentially take a very simple form. So this is the mixing of space-time, which I was talking about. And it looks like a rotation. I mean, it looks like a rotation in the sense that if you rotate the x and y axis in the Euclidean plane, that rotation is described just by, instead of hyperbolic functions, you have geometric functions, sine phi, cos phi, etc., etc. And the important thing is that, and this is the key point, that this transformation, which is a group, okay, leaves this object invariant. So if you take ct prime square minus x prime square, it is the same as ct square minus x square. Okay, so we learned that there is this whole issue of symmetry between moving observers, and the symmetries are basically related. They form a group. These are the Lorentz transformations, and these groups leave a certain object invariant, and that is this distance over here. And this last sentence over here of the invariance of this ct square minus x square for all inertial observers is actually due to Hermann-Minkowski. And the last point here on this slide is that the E and B fields also transform, so that Maxwell's equations are all invariant under these transformations. And I didn't write down these transformations. In fact, I had them previously, but they're all too complicated actually to write in terms of E and B fields. So you'll find it in the textbook. So this is the final slide of the special theory of relativity. Is the slide about Hermann Minkowski, who was Einstein's teacher. And it is he who introduced geometry into special relativity, which played a fundamental role in the general theory of relativity. So he says that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. So I explained all that to you in the last slide, but I just wanted to flash Hermann Minkowski's quote and his picture over here. So as I said before, that this is the infinitesimal distance in Minkowski's space, as opposed to this very simple infinitesimal distance in ordinary Euclidean space, which you are very familiar with. Okay, so that is the end of the special theory of relativity. Okay, let me move on. So given that the speed of light is the same for observers in relative motion, there can be no action at a distance which is simultaneous for all inertial observers in relative motion. So this idea of instantaneous gravitational interaction, which is present in Newton's law, is simply not consistent with Maxwell's equations of electromagnetism and the special theory of relativity. So hence Newton's law of gravitation needs to be modified. And I think this is a great story over here. I encourage everybody to read about it. It's very nicely written about in Abraham Weiss's book, Subtle is the Lord. It's a biography of Einstein. So waging one of the great struggles in modern scientific history, in 1915, Einstein completed the general theory of relativity, which is a theory of gravity in which the force of gravity is not instantaneous. And it is communicated at a finite speed, the same speed c, by changes in the geometry of space-time. I'll explain all this to you as we go on. And here the role of the electromagnetic field, which, communicates electromagnetic forces, is played by the metric of space-time, by some tensor that describes the geometry of space-time. I'll explain all that a little bit later. Now, I want to tell you a little story actually over here, which is very important, that in 1915, Einstein was invited by the Berlin Academy to deliver lectures on the general theory of relativity. There were 3 lectures. And you won't believe it that the equations he wrote down in the first or second lecture were actually wrong. It's only in the third talk, and I'll explain to you why also later on, that he really found the right equations. And, this story is very inspiring because, it is not like, like a great genius in which, like some God spoke to him and he wrote down the equations. And, I think it's an enormous struggle that Einstein went through literally for about 10 years, and certainly from 1907 to 1915 to discover the laws of general relativity and the modern theory of gravity, classical gravitation. Okay, now there were 2 puzzles over here. One of them I have mentioned already, that force of gravity is instantaneous. Newton's theory that cannot be consistent with special relativity. So, I had mentioned this also before, but let me just say it again. Einstein would like to have the force of gravity communicated by the speed of light, by a field which is analogous to the electromagnetic field. Now, to arrive at what that field is was a great story, and actually some part of it I'll tell you. And special relativity is sort of restricted to frames which move with respect to each other at constant velocity. See, it doesn't include accelerating reference frames. Einstein wondered why. Laws of physics must be invariant for all types of transformations. So these are the 2 puzzles about instantaneity of the force of gravity and the restricted invariance of special relativity that prompted him to think about the general theory of relativity. And a possible resolution occurred in 1907. I'll explain that a little bit in more detail later on. He called it the happiest or the luckiest thought of his life. The effect, and the thought was the following actually, the effect of a constant uniformly accelerated frame. There is a suggestion over here that what you call gravity is something which you're familiar with. For example, if you're sitting in a car and it brakes very sharply, you fall forward, right? Einstein is basically saying that fall forward is in a sense the same as something that falls by what you say is due to the attraction of the gravitational field of the Earth. Okay. Now, patching up small regions of space-time, as I'll explain to you, to construct the full space-time needs Riemannian geometry and also the mathematician, his friend Marcel Grossmann. Okay? So, let's move. So now I just want to give you a small tutorial on elementary differential geometry and how then it applies to the space-time geometry. Space-time is very important of general relativity. So here is a very simple little thing that you appreciate. But there are 2 bugs, I chose bugs because they're so small that they don't really feel the 3rd dimension. The whole world is the 2-sphere, okay? It's a 2-sphere of some radius r. And they are walking along geodesics. These are the longitudes which you are familiar with. Now, they're geodesics for reasons which I may explain later. A sphere. Now, these bugs are just walking along these longitudes, these geodesics. And as they're walking, if they walk for a very small time, short distance, they don't see any difference between the sphere and the Euclidean plane, which is just flat. Okay. So So in more mathematical language, here is a manifold, and the tangent space, Euclidean. So in the small, this manifold can be patched up, patches of Euclidean space, and the connection between these patches is the whole subject of differential geometry. All right, so as I said, there were small distances. Small means small with respect to the radius of the sphere. Okay, that's small and large always relative. The walk appears to be in flat space. Only after walking for a while, the bugs notice that they are walking on a curved space. They are sort of coming together without any force between them, and they actually meet at the North Pole. Here there is a very deep idea which I want to now turn to. Okay. So how does this type of very simple idea apply to the theory of gravity? So this is the beginnings of the general theory of relativity. And I've taken this very beautiful illustration from a book which I think is very good, very beautiful book by Kristen Needham on visual differential geometry and forms. So here is the book. So there is the Earth. And there is a person very, very far away from the Earth. The gravity is very weak. And the idea is the following, that that person there is surrounded by essentially a sphere, on which there are small beads, maybe of steel or whatever it is, something massive. Doesn't matter what it is. And they're all at rest at some point, this whole thing. And then they go and they start falling in the gravitational field of the Earth. So to this observer, it's a free fall, so she doesn't really notice any gravity. It's a free fall. So the key question is that true that the equivalence principle tells you that in the small, everything is just like in special relativity. But if you move for a longer time, how do you, in this way of looking at it, find out experimentally that there is a gravitational field? Or how do you describe geometrically that there is gravity? She doesn't have to look down to notice that she is falling towards the Earth. Look up. And what you find, and this is the key point, that this thing which was a sphere, and they were all at rest, starting to fall towards the Earth, this sphere basically turns into an ellipsoid. An ellipsoid whose exactly the way I've drawn it, not the other way around. You see that the particles which are horizontal to her start moving towards each other. The particle on top looks as if to her, as if it's going away. And the particle at the bottom looks as if it's going away down. This is really the key point, that without looking down at Earth, she can infer that she is in the gravitational field of the Earth. There is a change in the geometry. There is a gravitational tidal force, as I will not explain all these things, that you can infer without knowing that you are in a gravitational field of the Earth. So this is a very important point, and this leads us next to exploring how to describe the big mental jump from trying to describe this type of phenomena in terms of the geometry of curved space. Okay, I'm just trying to motivate. Okay, I mean, at some level, it was just an amazing insight of Einstein that gravity is somehow related to undulations of geometry that led to the final theory. Now I want to play a little game with you. I want to derive Einstein's equations in one shot for you. You see, I mean, I don't want to go into all the deep things that people talk about. I'll do it as follows. So So let's do it as follows. Okay, so let's recall Maxwell's equations, right? Now Maxwell's equations can be written in a very nice form by organizing the electric and magnetic field in this matrix. Okay, and this matrix F mu nu is antisymmetric matrix. Okay, that you can easily see this is minus, this is plus, this is minus, this is plus, etc. Okay. And then if you write Maxwell's equation in terms of this matrix, it's a good homework problem if you don't know it, is that d by dx mu of this tensor is the current. And we saw that the current is the charge density and the space component of the current. So these are Maxwell's equations. Anybody could have written it down, right? Post factor. So there are fields, and these fields F mu nu are sourced by the current. And the important point is that this immediately tells you that this current is conserved, the charge is conserved, because F mu nu is antisymmetric. Okay. So, I mean, if I'm a very smart physicist, mathematician type of guy, you know, some people I know like that, I won't name them, they're good friends of mine. So how do you describe electromagnetism? Just look at the tensor and construct a tensor out of electromagnetic fields and take its divergence, because then you get a vector, that is the current, and it's conserved by construction. Okay, let's apply this type of logic to Einstein's equations. So now gravity is sourced by matter. So what sources matter? Physicists know it's the energy momentum tensor, right? This energy, static energy plus energy which is moving, which has momentum, right? So there's a tensor, you know, it's something which has nice transformation properties, but the important point is it's symmetric tensor, okay? And it's a tensor in curved space. That's an added thing which you should keep in mind. It sources the gravitational field, that is, sources the metric. Now, how am I supposed to invent an equation that this type of thing happens? And here is the point. So what you do is you form a symmetric tensor, which is called, I'll explain this to you a bit later, what is called the Riemann tensor. It's a four-legged object. It is antisymmetric in the first two and the last two, but is symmetric under the interchange of the first two and the last two. You look at this object, which I will explain to you a bit later, and then form something which is a symmetric tensor over here. You know, because T mu nu is symmetric, I should form something symmetric, okay? It's, of course, has a name. It's called the Ricci tensor, invented by a mathematician called Ricci. And then I form what today is called the Einstein tensor. That is R mu nu minus, subtract this off. Okay, and why do I do that? Because if I take the divergence of this, the covariant divergence of G mu nu, it is zero. Just like the covariant divergence of the stress tensor, energy momentum tensor is zero. So here you are. I can write down this object is equal to this object up to constants. And these constants are very easy to determine from Newton's law of gravitation. So here you are. These are the Einstein equations. Now let me tell you the mistake Einstein made in the second lecture, November 1915. He forgot this term, the second term. Okay, the second term over here was not there. So if you take the covariant divergence of both sides, you get a contradiction. Anybody who is doing graduate work in physics or undergraduate work knows this today, but Einstein made that mistake. And if you don't have the second term, then you don't get as a limit for low velocity motion, Newton's laws of gravitation. So as you know, in physics, you always have to be consistent with what went before. Okay. So when certain parameters are taken small, you get the previous laws back. Okay. That's why, as Feynman emphasized many times, science is very difficult because it has to be consistent always with what went before. Okay, so this, one more thing I want to point out over here, that the value of Newton's constant in CGS units is approximately 10 to the minus 8, okay, in appropriate units. And, but Gn is divided by C4. So if you take the speed of light to be something like 3 times 10 to the 10 centimeters per second, and you get a factor of 10 to the minus, this object is something like 10 to the minus 48 that sits in front of T mu nu. And this is extremely significant point. That the coupling of gravity to matter is extremely weak. I'll come back to it later on during the lectures, but just keep this in mind. Okay. All right. Now, let me just did this. Okay. So this is some pictures again. So general relativity describes the changes of the geometry of space-time caused by massive objects to which other objects respond. And there's a very famous quote from John Wheeler that says that matter tells space-time how to curve, and curved space-time tells matter how to move. And as I said before, the number of 10 to the minus 48 in front of the stress tensor in the Einstein equation actually leads to a very important observational fact that space-time is like an elastic grid. It is communicative, causal, but very, very stiff. It is approximately 10 to the 20 times stiffer than steel. This is why we couldn't discover gravitational waves for 100 years. I mean, if you wave your hand and if you dance around in a room, you're emitting gravitational waves for sure. But it's suppressed by that factor. And it's only when huge objects like black holes collide that you can produce gravitational waves which can be observed actually. Okay, that's just an aside. We'll come to all that later on. So in a curved space-time, an object follows a path which I mentioned to you. So let me just show you this animation which I stole from Juan Maldacena's talk. Very nice. So it's like a trampoline. It's like a heavy object, the sun. It distorts the space-time around it. Now in these pictures, it's always space that looks distorted. But the most important point here is that it is not only space distortion, but time distortion also, which I will come to a bit later actually. Okay. All right. Here it is. So Einstein's theory has a very important message about the flow of time. And this is, again, an animation I have borrowed from Juan Maldacena's talks. It says that if gravity slows down, gravity slows down as you approach large masses. Okay, so near the surface of the Earth, the clock is moving very slowly, but as you go higher and higher above, the clock moves faster and faster. Now, of course, I mean, you use this effect all the time on your cell phones. Okay, this is one of the corrections the cell phone technology takes into account actually to give you a very good GPS. It's amazing. No? Einstein's general theory of relativity and special theory of relativity are important for you to know where you are. Okay, so this is about time. Now let me, some particular slide, I don't know whether I forgot or something happened. Sorry. But how long do I go on? I'd like to know that.
So you can go on for a while. I think since we started late, you can go on.
Okay, I'll do that.
Yes.
Now, I just wanted to very briefly end this talk with 3 simple tests of general relativity. See, we realize that Maxwell's theory is a good theory because it's not only theoretically very deep and robust, but it's also agrees with experiments. Okay, it's very important. That was the cornerstone of the special theory of relativity. But Einstein came up with general relativity without the help of experiments. It's quite amazing. By trying to resolve internal contradictions of Newton's theory of gravity. And so there are 3 famous tests of general relativity. The first is the test of what is called the gravitational redshift. the wavelength of light shifts from blue, which is short, to red, long, as you climb in a gravitational field. I mean, if you think of light in terms of photons, it's obvious because, as it's climbing, it's losing energy, so it's becoming more and more long wavelength and shifted towards the infrared. Okay? And so you can actually measure all this, okay? And this was actually first measured in an experiment by Pound and Repka in 1959 at Harvard. In fact, in the Harvard physics department, they have a plaque mentioning the Pound-Repka experiment in the building where they did it. And there are also astrophysical tests by looking at the light from the sun, from white dwarfs, from neutron stars. And in fact, in some sense, our understanding of the expansion of the universe and the recession of the galaxies comes from, experimental observations of the red shifts. The red shift is this phenomenon that in a gravitational field, you lose energy and the wavelength of light becomes longer and longer. The other test was, of course, very crucial and extremely important test, and that was the test which Einstein became very famous afterwards, and it is the bending of light by massive objects. Okay, so because light carries energy, and if you have a very massive object, it will certainly bend the light. Okay, and the Newtonian theory, of course, is a theory of gravity, so it also has a prediction for this angle by which this bending takes place. And this angle turns out to be 0.9 arc seconds. Okay. But the Einstein theory predicted a result which is twice the Newtonian theory result. Okay. And it agrees with experiment. And these experiments were carried out during a solar eclipse. This is the famous Eddington experiment of 1919, which made Einstein famous. I mean, that he has toppled Newton's theory of gravity. And there were other experiments that followed and confirmed all these things, which I have listed over here. Okay. Then also in the 1960s, this long baseline radio interferometry gave most accurate verification of the general relativity prediction. And when asked by an assistant if general relativity had not been confirmed by Eddington and Dyson in 1919, Einstein famously made the quip, "Then I would feel sorry for the dear Lord. The theory is correct anyway." Okay, so the third test, which is very well known, is the so-called perihelion of Mercury, which basically says that if you look at the Sun-Mercury system, then the elliptical orbit actually precesses. Now there is a prediction for the precession from the Newtonian theory, which I have mentioned here, predicts a precision of so many seconds of arc per century, 5,557. And there's a discrepancy of 43 seconds of arc per century. And Einstein's theory actually really would resolve this discrepancy. And I think with these three experiments in the early years, the theoretical predictions of Einstein's theory of general relativity were very well established, and it's a good established theory of gravity. Okay, very good. Now that we have a good theory of gravity, but let's recollect actually what is going on. What we have, there's one slide I forgot to include, but that really bothers me. But I explained in that slide, properties of curved space-time and stuff like that, but never mind. Maybe I'll flash it tomorrow. So we have a framework. That's the main point. What is the framework? The framework is curved space-time. So the classical theory of the world is constructed in a curved space-time. The curved space-time is locally obeys all the laws of special relativity. Okay, it's physics is Lorentz invariant and all that in that local neighborhood. I explained that to you in terms of that bug walking and all that stuff. But in the large, there is curvature. And there are gravitational tidal effects which enable you to understand gravity in terms of these tidal effects or the undulations of space-time. So that's the framework. And this is the framework in which physicists today understand the expanding and accelerating universe. It is this framework in which they understand gravitational waves. And it is in this framework that they understand black holes, which are solutions of Einstein's general theory of relativity. So GR is a framework to discuss cosmology, gravitational waves, and black holes. And by now, these applications are experimentally extremely well confirmed. So I think I'll stop here today, and maybe we can take questions.
Thank you, sir.
Next up is yeah.
Yes, sir.
Yeah, all right.
So I think start off with questions. First, we can ask the people who are in the meet,
Yes.
the participants in the meets. If any of you have a question, you can either unmute and talk or put it in the chat box and we'll read it out. Okay, so I think then, so there was a slight echo. Yes, I think then I'll start off with a question of my own to begin.
Sure.
So you talked about the ellipsoid forming for a free-falling person.
Yeah.
So could you expand a little bit on why the ellipsoid is formed? Why do the things move closer to each other like this horizontally?
Yes. So, let's go there.
Yes.
Here, right?
Yes, sir.
Yeah. Can you see the slide?
Yes, sir.
Okay. Now, what I was saying is the following: that suppose we don't know general relativity or anything at the moment, but we know about Newton's law of gravity. So there is this Earth, and the Earth actually is a very huge, massive object. And so there is a gravitational field actually. And that gravitational field is not uniform. And this is very important actually. Because if the gravitational field is uniform, then you will not feel any gravity. That is the essence of the principle of equivalence, right? So the question is, how do you notice the effects of gravity without looking out of the window and seeing that you're falling towards the Earth? So here's the point. So because the gravitational field is not uniform, these arrows which show you there's a squeezing towards the center, right? So if you assume that Earth has a gravitational field which is not uniform, this is quite clear actually. If you also look at the particle at the end, it is obviously falling faster than the person inside, right? And it is, and if the person looks up, the particle actually on the top looks receding in the upward direction. So this is why the sphere becomes a ellipsoid. It is very much like the way that the tides are caused actually by the gravity of the Earth and the Sun.
Thank you, sir.
Is that,
yes, sir, I understand. We have two more questions.
Yes, we have two more questions from the audience and one question from my side. So first, the audience question. The force of gravity is not instantaneous but travels at the speed of light. So that would mean the motion of the Earth is the effect of the sun. The motion of the Earth will feel the effect of the sun a few minutes before. What if the sun just disappears for a moment, but the Earth would be affected after a few minutes, only after a delay? So that would mean the Earth will still be in a continuous motion that is accelerating, but without a cause. So does that mean Newton's first law is wrong in that scenario?
I didn't understand. You're saying that we have the Earth-Sun system and the sun suddenly disappears.
Yes, sir. So I think the person is saying that since in this situation, the Earth is still accelerating, but there is no force acting on the Earth.
Yes.
Yes.
So the only 8 minutes after this.
Yes. But for that 8 minutes,
that you will know that the sun is gone, and then you are a wanderer somewhere. You will be attracted by Jupiter, maybe. I don't know.
So I think the question is that for the 8 minutes, I think the question means that for that 8 minutes, there's no source of force. There's no force acting. I think the question is that there's no force coming from the sun. There's no source of force, but the Earth is still accelerating, at least for that 8 minutes, till it feels.
Yeah,
so,
but what I'm trying to say is that what I'm trying to say is that the Earth will continue as it would be with the sun there for 8 minutes. So it's only after the 8 minutes that you will not feel the light or the gravity, right?
Yes. Okay, I hope that I would not know if that clears the question, but I think that's fine. Okay, so the next question that was asked was, by special theory of relativity, we know that time passes slowly for moving objects. Then in the photon's frame of reference, which is moved at the speed of light, time seems to stop. So does that mean that photon takes 0 seconds to move from one point in space to another? Or does it mean that the 2 points in space are the same for the photon?
You said that we have to jump into a frame to move with the photon. Is that?
Yes, frame that's at the same speed as the speed of light.
Yeah, but we cannot do that because, if I am a material laboratory with a certain mass, I can never reach that speed really, right? Because the effective mass of that apparatus will basically become larger and larger and larger. And I will not be able to reach that speed, right? So in fact, this is a very famous question which Einstein asked, that how will light look like if I run with respect to it?
Yeah.
But
I think this question is related to that.
But can you just repeat the question again, because there's something very strange about it. Tell me.
Okay. Yes, sir. Okay. If then in the photon frame of reference, which is moving at the speed of light, time stops. So does the photon take 0 seconds to move from one point to another point in space? Or does it mean that the 2 points in space are the same for photons?
Why do you say time stops? I don't understand that.
I'm not sure what's meant.
What do you mean by saying time stops? Time doesn't stop.
I think we can ignore just that part, just photon frame of reference, which is moving at the speed of light. Then in that case, what does it seem like? Is it that it takes 0 seconds to move from one point to another, or is it that the 2 points in space are the same?
No, it will not take 0 seconds. I mean, it will just keep on moving at the speed of light. And I will make an observation that it has done that. And I don't understand why it will take 0.
I think the question is from the frame of reference of the photon itself.
Or from the view of the photon. I mean, if I am the photon, how does the world look like to me? Is that
Yes.
I don't know. I mean, but I can tell you what it really looks like to me, because I have an, if you want to measure something, you need to have some mass, right?
Yeah.
And I think a laboratory with even any amount of small mass also cannot reach the reference frame of the photon. Not possible to do that.
Then there are a few more questions. Okay, so how exactly does the metrics, the metric play the same role as the EM field? Is it that their tensor equations are similar?
No, the equations are not similar. In fact, the equations are nonlinear. The equations of Maxwell are linear equations, as we saw, but the equations of general relativity involving the metric are very nonlinear functions of the metric. So, so that's one point. But the abstract idea is very similar, that there is matter which sources the metric by some equations, then there is charged particles which source the electromagnetic field by some equation. The equations are vastly more difficult in general relativity.
Thank you, sir.
Sir, there's one more question. There's a simultaneity convention that Einstein introduced, and he said that the concept of simultaneity at a distance cannot be conceived without a convention. Can you elaborate on that?
Without a convention. I mean, Einstein's main point was there is no simultaneity for observers who move relative to each other. That is the main point, right? That's what I explained in that little spaceship example of a person on the ground watches a certain beam of light in a spaceship, and what does she see, and the time dilation that happens because of that. Simultaneity is violated, that's the main point.
Mm-hmm.
So I think the question is asking what exactly the conflict, how can you define simultaneity?
Oh, how can you define simultaneity? Okay, now that. I mean,
at a distance.
It's not a problem. I mean, think of the following. Suppose you have a person standing at a railway station, and suppose there is a train, and at the front and the back of the train, there are two light bulbs, and there's a switch. You put on the switch and the bulbs go on together. That's simultaneous. That's simultaneous for the engine driver. But now if the train starts moving, and moving faster and faster and faster, approaching the speed of light, for the person at the platform, it won't be simultaneous. So that's the main point. There'll be a time delay. Yes, sir.
Right? Okay, so there's one more question. So if there's a gravitational body and you observe a redshift, how can we be able to tell the difference between that and if it is because of Doppler redshift, for example, for a body that is at a significant distance? If we observe a redshift, will we be able to tell that it's due to gravitational redshift?
You can differentiate these things experimentally. Now, I don't know the details about this, but certainly you can. Yeah. Certainly.
Okay.
Yeah.
Okay. I think right now these are the questions that were.
In the meeting, if there's any participant who has a question, you can ask your questions. Okay, I think, sir, then that's for today. We don't have any more questions.
Okay.
Yes, sir.
All right.
So I think, yes.
Okay, we meet tomorrow. Tomorrow we
Yes.
meet.
Yes, sir. So we'll just say a few closing words as well.
Okay. All right.
Good.
Okay. Thank you.
Thank you. Thank you, sir, for that very enriching lecture. We look forward to the coming days for the lecture, since the series seems to be off on a good start.
Okay. All right. Thanks.
Thank you.
Thank you, sir. And thank you, everyone, for joining. We hope to see you tomorrow.